Cycloaddition reaction is going to be the topic of this lesson. And the last lesson we talked about Diels-Alder reactions, which is a specific type of cycloaddition reaction. And it really makes a great launching point for talking about them in general. And we're going to talk about things like thermal conditions versus photochemical conditions. We'll talk about suprafacial and antarafacial. We'll talk about symmetry allowed and symmetry forbidden. And we'll introduce what's known as frontier molecular orbital theory. And I'll pay allegiance to what you might have been presented in your class as the Woodward-Hoffman rules. Now, I'll warn you, this is a rather difficult section to both teach as an instructor as well as to learn as a student, but I promise you by the end of this, you will have a much better handle on cycloaddition reactions. Now, this lesson is part of my organic chemistry playlist. I'm releasing these lessons weekly throughout the school year, so if you want to be notified every time I post a new lesson, subscribe to the channel and click the bell notification. All right, so cycloaddition reactions. I want to revisit the last lesson, and right at the end of that last lesson on Diels-Alder reactions, we talked about the conservation of orbital symmetry, and I just want to go back over that for just a second. So we kind of took a look and said, yeah, typically when we're doing one of these reactions, we're looking at the highest occupied molecular orbital of the diene and the lowest unoccupied molecular orbital of the dienophile, and we're transferring electrons from the HOMO of the diene to the LUMO of the dienophile. And it is these molecular orbitals, part of the frontier molecular orbitals, so a term we use to kind of describe the HOMO and LUMO. But that's going to be what needs to actually match symmetry to be a symmetry-allowed reaction. And if they don't match, it'll be a symmetry-forbidden reaction. And one thing you should realize, though, is that saying something is symmetry-allowed and symmetry-forbidden doesn't mean like it'll happen or it won't happen. It's kind of like if you have an 11 o'clock curfew as a teenager or something like this. If your parents give you an 11 o'clock curfew, for most of us, that doesn't mean that we'll never stay out past 11 o'clock. It might mean we're less likely to, but every once in a while we might not follow the curfew. So it's got kind of a thing. So symmetry allowed means it's probably going to be leading to the major product, whereas symmetry forbidden doesn't mean it won't happen. It just means it's probably going to have a higher activation energy. It has this symmetry barrier, we say in it, and it's probably going to be leading to a minor product instead. So let's take a look here and take a look at the HOMO of 1,3-butadiene and the LUMO of ethylene here. And you might recall that they alternate whether they're symmetric or antisymmetric. And so here we've got symmetric, antisymmetric, symmetric, antisymmetric, symmetric, and antisymmetric. And that's why the Diels-Alder works, it turns out, is because both the HOMO of the diene and the LUMO of the dienophile are both antisymmetric. So now we could draw out the entire HOMO of 1,3-butadiene and the entire LUMO of ethylene, but the truth is we only really need the ends where we're forming the new sigma bonds. And that's what I'm going to restrict myself to drawing. And what's nice is if they're symmetric, it just means that the ends are going to match. And if it's antisymmetric, then they'll be opposites. And that's a nice, convenient thing. And as long as you remember that the even numbers are antisymmetric, the odd numbers are symmetric. So notice psi 1 here and psi 3 are symmetric. Same thing over here, psi 1, and then psi 2 and 4, and then psi 2 star over here, all antisymmetric. So it's nice, convenient for remembering which are symmetric and antisymmetric. So if we again look at the diene for 1,3, look at the HOMO, I should say, for the diene. So it is antisymmetric. And so the ends here are not going to match. Now, often you're going to be on the hook for actually drawing the entire molecular orbital. And in this case, you'd be like, well, it has one node. And if it has one node, well, then these two would be the same and these two would be the same and so on and so forth. But again, I'm going to focus on the ends because I just want you to be able to predict products and predict transition states and things of this sort. So that's going to be my purpose here. If we look at the LUMO, psi 2 star here, again, that is antisymmetric. And so the ends here are not going to match. And I'm going to draw this in such a way, though, so that we can line this up with the molecular orbitals matching up here. And so we see that we've got a match here and a match here. And so what's going to happen here is that these are going to rehybridize to sp3 to form bonds and things of this sort, but they've got to match for this to be what we call a symmetry-allowed process. And they've got to match on both sides. Now, the way this works, on the left-hand side, so if you're going from bottom to top on this side and bottom to top on this side, we refer to that as being suprafacial-suprafacial. So suprafacial on both sides, if you will. So, and the way this really is working, so the diene here is interacting, forming overlap here from the bottom side on both ends, so that's suprafacial. And then the ethylene here, same thing. It's interacting from the top lobes on both sides, so it's also suprafacial. And so the suprafacial here designation refers to both reactants. And since we got two reactants, that's why you've got two designations. Now that's suprafacial, and we'll contrast that a little bit later with what's known as antarafacial, where you actually interact with the top lobe on one side, but the bottom lobe on the other side, and we'll see kind of how that works. But for now, this is suprafacial-suprafacial, and as long as these have the same symmetry, and again, these were both antisymmetric, that will be what is allowed. Suprafacial-suprafacial will be the symmetry allowed, or simply, sometimes we just say allowed process, or allowed transition state, whereas suprafacial-antarafacial would then be forbidden in this example. All right, so that's under what we call thermal conditions as well. So oftentimes you might recall we said all our Diels-Alder reactions, we just do that little triangle. That triangle means heat, and really that's our way of signifying that we're doing this reaction under thermal conditions. So in all the Diels-Alders we looked at, they were all under thermal conditions. Well, now we want to take a look at cycloaddition reactions, which can be done under thermal conditions, but they can also be done under what's called photochemical conditions. And so we're going to irradiate them with just the right energy of light for the reaction we're doing. And our way of symbolizing that is using h nu. So if you recall, that's the energy of a photon, and it's our symbol for saying we're doing this under photochemical conditions. And what happens when you do this under photochemical conditions is you're going to promote an electron here on the diene. So in that, your electron's going to get promoted up from psi2 up to psi3 instead. And so no longer should we consider psi2 as the HOMO. Now it would be psi3 star. That would be the highest occupied molecular orbital. And so now it would be the transition going here. And so if we go and take a look at the symmetry now, so now we see that psi3 star being an odd number is symmetric, whereas psi2 star, the LUMO over here, is antisymmetric, and their symmetries don't match, and that's going to lead to a little bit of a different situation here. So once again, so psi3 star is symmetric, and if it's symmetric, again, I could draw the entire molecular orbital, and you might be on the hook for that. So, but we covered that in a different lesson. What I really want to just be able to do is draw the ends where the actual overlap is occurring. And so being that it's symmetric, these two are going to be the same at the ends. So, and then with psi2 star, the LUMO of ethylene is again antisymmetric. And all of a sudden we have a problem because we've got a match over here, but we don't have a match on this side. And so this is not going to be a suprafacial-suprafacial transition state because we don't have in-phase overlap resulting from that. And so it turns out one of these is going to have to kink. And it turns out it could be either reactant that's going to have to, what I'm going to call kink. Maybe that's not the best term. It's not a technical term, but it's the one I'm going to run with. And I'm going to choose this guy to be the one that kind of changes the way he interacts and gets overlap with this guy. So I'm going to kind of draw it at an angle. Okay, if we look at the interaction now, so here we're going to have bottom lobe of one to the top lobe of the other, but on the other side, it's going to go like so. And so for this guy's like bottom lobe, I'm suprafacial. But for this guy's like I'm interacting with the top lobe on one side, but the bottom lobe on the other, and it's antarafacial. And so we end up calling this the transition state in this case suprafacial antarafacial. Cool, and technically some people will actually say that antarafacial-suprafacial is distinct from this, and that would just mean that it's the diene in this case, that would be antarafacial, and the dienophile, that would be suprafacial. So, but the key is this, when the symmetry don't match, when one's symmetric, one's antisymmetric, like we had the case here, this is going to now be the allowed transition state. What would be allowed would be suprafacial-antarafacial. What would be forbidden would now be suprafacial-suprafacial. Now, technically, if you can do suprafacial-suprafacial, you can also do antarafacial-antarafacial, but for undergraduate, we usually kind of leave that consideration out. It's a little less likely and things of a sort, and we just leave it out of the consideration at all. But if you took this in a graduate level class, then you might also see that incorporated into the curriculum here. But I'm leaving it out on purpose, just an FYI. Cool. So in this case, under thermal conditions, suprafacial-suprafacial is allowed, which means that suprafacial-antarafacial would be forbidden. But under photochemical conditions, now it's suprafacial-antarafacial that's going to be allowed, and it would be suprafacial-suprafacial that would be forbidden. So one is always allowed, and the other is always forbidden. It always works out that way. And if the symmetries match, well, then it's suprafacial-suprafacial that'll be allowed. And if the symmetries don't match, then it'll be suprafacial-antarafacial that is allowed instead. All right, so let's take a look at what the effects of this might be, and we've got a nice convenient example to see what's going on here. All right, so this is the example we're going to learn, and this is one of the Diels-Alder, or similar to one of the Diels-Alder we covered in the last lesson. In this case, if we do this thermally, that's what you'd normally learned as part of your Diels-Alder. And in that case, again, the allowed product is the one you're typically going to predict. If you're asked to predict the product in a cycloaddition, you're predicting the allowed product. And again, the forbidden product would usually be a minor product. And so if you're asked to predict the product or major product, just predict the allowed one. And in this case, you learned with the Diels-Alder, and we predict the allowed product back in the last lesson. So we are going to form a 6-membered ring. So, and you learned that if these two groups are cis to each other on the reactant, then they're going to be cis to each other on the product as well. So there you go. You also learned that if these two groups, in this case, this one points out, the methyl group also points out, there's hydrogens that point in, and you learned that if both groups point out or both point in, they end up cis on the product as well. But if one's out and one's in, then they'd be trans on the product as well in a Diels-Alder reaction. And so we're going to hold that true as well. You also learned that these groups are all on the outside, end up cis all to each other, and we're going to keep that true as well. So we got a methyl group here, and a methyl group here. In this case, they're all dashes. They could also all be wedges. And if that was a distinct stereoisomer, we'd draw that other one as well. But in this case, this is a meso compound. You can see that mirror plane. And so in this case, you just get the one meso compound. Whether you made these all dashes or all wedges, it is the same thing. Now, if you do this under photochemical conditions, so now you're going to see something new. So, and it all depends on who gets to be antarafacial, because what you really learned here is that if these two groups are cis to each other, if it goes suprafacial, they'll still be cis in the product. And you learned here, if both of these point out or both point in, then they're going to be cis to each other in the product if, again, that reactant gets to add suprafacial. Whereas antarafacial does the exact opposite. And so in this case, we've got a couple of different options. Either this could be suprafacial and this antarafacial under photochemical conditions, or this could be, the dienophile could be suprafacial and the diene antarafacial. And so it leads us to a couple of different options for products here. And so in this case, this is one of your options. In this case, again, the two groups that both point out on the diene still end up cis. That must have been suprafacial. However, these two groups that were cis to each other end up trans on the product. That's where it was antarafacial. So one was suprafacial, one was antarafacial. It leads to this product. This is no longer a meso compound. So technically, you also get this guy's enantiomer, where these three are wedges and he's the dash, and that's one option. But you could have it the other way around. Instead of having the diene being suprafacial and the dienophile antarafacial, it could be the opposite. You could have the diene antarafacial and the dienophile suprafacial, and so you get one other set of stereoisomers here as well. And so in this case, now it's the dienophile, where they're cis and they still end up cis. That one's suprafacial. But here the two methyl groups both point out, and now they ended up trans, though, opposite of what we'd normally have predicted with a Diels-Alder. So, and under photochemical additions, I chose that one to be the one that went antarafacial. So big take home here is that what you learned in the normal Diels-Alder, that's what suprafacial does in terms of stereochemistry. And so if you've got a suprafacial-suprafacial transition state, you should know what that looks like based on that's what Diels-Alder does. However, if you've got a suprafacial-antarafacial transition state instead in any kind of cycloaddition, well, then that'll do the opposite in terms of stereochemistry for one of the reactants compared to what you saw with Diels-Alder. So that's kind of the deal here. So a couple of different sets of enantiomers here, 4 total different stereoisomers for the product under photochemical conditions, but one major meso product under thermal conditions. Cool. Now, it turns out this is a part of more broadly what we call frontier molecular orbital theory. And some people classify what we'll talk about next as part of what was known as the Woodward-Hoffman rules. So And I've mentioned it, that's all I'm really going to do. It turns out the Woodward-Hoffmann rules are actually much more complex than the simple version we're going to kind of introduce here. But it's also the more complex version is really something you're more likely to get in a graduate level or organic class, not in something in your undergraduate class. So I'm paying lip service. Technically, what we're talking about is part of the Woodward-Hoffmann rules, but I'm just going to call it frontier molecular orbital theory, and we'll go from there. Now, if we take a look at the reaction we just did, and we kind of show the movement of electrons. So here we've got 6 electrons moving. We would call this a 4+2 cycloaddition, where we've got 4 electrons moving in the transition state from one reactant, 2 electrons moving in the transition state of the other, for a grand total of 6 electrons. Now it turns out this would be an example of what we call 4n plus 2 pi electrons. So 4n plus 2 is just a mathematical term. It describes an infinite set of numbers, where n here can be any integer starting with 0. So if you have 4 times 0 plus 2, that's 2. If you have 4 times 1 plus 2, that's 6. If you have 4 times 2 plus 2, that's 10. So essentially what you can do is you can just start with 2 and then add multiples of 4. So 2, 6, 10, 14, 18, all the way up to infinity. Any one of those numbers is called a 4n plus 2 number. I personally like to also think of it, and a lot of students do, as an odd number of pairs of pi electrons. So notice 2 electrons would be 1 pair, an odd number. So 6 electrons here would be 3 pairs, an odd number. 10 electrons would be 5 pairs, an odd number. So that's another way to think about this. Instead of looking at it as 4n plus 2 pi electrons, so which describes an infinite set, which is, great if you're a mathematician, but not so great if you're anything else. So if you just think of that as being representing an odd number of pairs, great. So, and it turns out when that's the case, so you can actually make some generalizations. When you've got this odd number of pairs, it turns out that the symmetry of the HOMO and the LUMO are always going to match, which means that suprafacial-suprafacial would be allowed, and suprafacial-antarafacial would therefore be forbidden. And it's a great thing. However, you'll find out that if instead of 4n plus 2 pi electrons, your other option is 4n pi electrons, you can think of this as an even number of pairs. And so we'll find out, we're going to take a look at the 6 plus 2 cycloaddition in a minute, which is 8 total pi electrons, a multiple of 4. 4n just means multiple of 4. We'll take a look at a 2 plus 2 cycloaddition in just a minute as well, which would be 4 total pi electrons, which again is a multiple of 4. And whether you want to look at this as a multiple of 4, 4, 8, 12, 16, 20, or as an even number of pairs. Notice 4 electrons would be 2 pairs. 8 electrons would be 4 pairs, so on and so forth. Regardless of how you want to look at that, so whether it's a multiple of 4 or an even number of pairs of pi electrons moving in the transition state, so in that case, the symmetry of the HOMO and LUMO are not going to match. And so if the symmetry doesn't match, well then under thermal conditions, the suprafacial-antarafacial so ends up being the allowed transition state, whereas the suprafacial-suprafacial ends up being forbidden under thermal conditions. But then under photochemical conditions, you always get what's opposite of your thermal conditions. So going back to your 4 plus 2 here again, which is an odd number of pairs, a 4n plus 2 number, notice that suprafacial-suprafacial was allowed under thermal conditions, which means that suprafacial-antarafacial was forbidden under thermal conditions. But under photochemical conditions, it's the opposite. Now it's suprafacial-antarafacial that's allowed, and suprafacial-suprafacial is forbidden. Well, again, if you're doing like a 6 plus 2 or a 2 plus 2, now you're going to find that it's suprafacial-antarafacial that is allowed under thermal conditions. So whereas under photochemical, it would be suprafacial-suprafacial that would be allowed. So it's just the opposite. So we've really got, this is your big source of confusion here, is we've got the number of pi electrons, you got 2 options there, and they're opposites in terms of what's allowed and forbidden. But then for each set, you've also got thermal conditions and photochemical conditions, which are also opposites of each other, and that's kind of the rub. Now, if you remember that your Diels-Alder is an example of the 4n plus 2 number. So, and we saw that with conservation of orbital symmetry, it goes suprafacial-suprafacial is what is allowed under thermal conditions. If you memorize that one, you can make all the rest kind of fall into place, because if Diels-Alder is suprafacial-suprafacial is what is allowed under thermal conditions, well then it would be suprafacial-antarafacial that would be allowed under photochemical conditions. And if you know what's allowed in each case, then you know that the opposite is forbidden. And then if you say, well, instead of a 4n plus 2 number, if it's a 4n number of pi electrons, then it's exactly the opposite of what you know about Diels-Alder. So that's kind of the deal. Let's take a look at that 6 plus 2 and 2 plus 2 cycloaddition. All right, so next reaction we're going to take a look at here is with 1,3,5-hexatriene and ethylene. And in this case, we've got 6 pi electrons here, 2 pi electrons here, and this is going to be an example of a 6 plus 2 cycloaddition. And if we look at the movement of electrons, forming a new sigma bond here and here. And so in this case, we'd form an 8-membered ring. Looking like so. Cool. Now in this case, it turns out whether we're doing this thermally or photochemically, we really couldn't tell the difference. And again, the big difference comes down to stereochemistry when you start attaching substituents either to the ethylene here or to the ends of the conjugated system here. So had we had like 2 groups out or 2 groups in, or 2 groups that are cis or trans here, we would then tell the difference. We'd be able to figure out, did we go a suprafacial-suprafacial transition state or suprafacial-antarafacial transition state. So, but in this case, I don't have any of those groups. This just has 2 hydrogens, this has 2 hydrogens, this has 2 hydrogens, 2 hydrogens. And so there's no distinction here. And so whether we did this thermally or whether we did it photochemically, we wouldn't notice a difference in this case. So, however, we could still determine what kind of transition state we went through based on now what we've learned. So if we take a look here, so with 1,3,5-hexatriene, you can see with 6 pi electrons, so here psi3 would normally be the highest occupied molecular orbital. And then again with ethylene, so all I really need to know is that it would be psi2 antibonding, that would be the LUMO. Cool, and so in this case, notice one's an odd number, one's an even number, and if you might recall, that means the symmetries are not going to match. So in fact, we can take that a step further. Psi3 here being an odd number, so you go symmetric at psi1, anti-symmetric at psi2, symmetric again at psi3. So in here, psi2 is going to be anti-symmetric. So, and when your symmetries don't match, that's when your allowed transition state is going to be suprafacial-antarafacial, as we'll see the necessity for here in a sec. So if we go through, and again, I could fill in the entire molecular orbital, and in fact, if you've got the study guide handy, I did there. But the key is, I really only got to fill in the ends to predict what kind of transition state. And so again, if this is symmetrical for psi3, so that tells me that the ends are going to match on a molecular orbital. So we're good to go there. So, but on the other one here, the LUMO, it's anti-symmetric, so the ends here don't match. And so in this case, we see that suprafacial is just not going to work. It'll work on one side, but it won't work on the other side. That's why suprafacial-antarafacial would be allowed, and suprafacial-suprafacial would be forbidden. Cool, so it wouldn't work just as we've drawn it. I have to kink one or other of the reactants, make one of them antarafacial addition. All right, so what if we do this under photochemical conditions? Well, once again, remind yourself that under photochemical conditions, you're going to promote electrons here from psi3, at least one electron from psi3, up to psi4. Technically, psi4 shouldn't be higher than psi2. I'm not drawing this well, but we will promote an electron up there under photochemical conditions. So, and now that's going to be an anti-symmetric orbital. And so now both psi4, the new HOMO, let's cross that out. This would now be the HOMO under photochemical conditions, and they're both anti-symmetric. And when the symmetries match, that's when suprafacial-suprafacial is going to be allowed, and when suprafacial-antarafacial would be forbidden. And so once again, these are both anti-symmetric, and what that means is that the ends are not going to match. And again, you can draw the entire thing, and you might be on the hook for that. You should know how to draw all those molecular orbitals. We did that a few lessons ago. And they're on the study guide, but I'm only going to take the time to do this. Again, my goal here is to help you predict products. All right, but now we can see that we got suprafacial-suprafacial being allowed based on the symmetry, which means suprafacial-antarafacial would be forbidden. Cool, and so now we know how to predict what's allowed and what's forbidden. And if we had to worry about any stereochemistry, we just have to know that suprafacial-suprafacial does what Diels-Alder does, because that's what it is. Whereas suprafacial-antarafacial, the reactant that goes antarafacial, does the opposite stereochemistry-wise of what the Diels-Alder did. Cool. So that's the 6+2 cycloaddition. We'll see one little special thing about the 2+2 cycloaddition now. All right, so now we're going to try and react two ethylene molecules together. This would be known as a 2+2 cycloaddition. Our motion of electrons would look like so. Trying to form a new sigma bond right here and form a new sigma bond right here. And so the hope is so that we could create just plain old cyclobutane. And we're going to find out in one of these cases, though I've drawn it in right now, I'm going to erase that in a second and write no reaction. We're going to find out in one of the cases it's not going to work. And we'll talk about why that is in just a second. So just keep that in mind. I drew these in, but I'm going to erase one shortly. All right, so if we take a look at what's going on with our HOMO and LUMO, our frontier molecular orbitals here. So in this case, for this one, let's use the highest occupied molecular orbital, and with just 2 pi electrons, that would be Psi1. Let's put this on the other side, make it match up what we did earlier. So there's our highest occupied molecular orbital for this one. And then I'll use the LUMO for the other. Notice they're identical, so it didn't really matter which one I chose to be use the HOMO and which one I chose to use the LUMO. So, but in this case, the LUMO is going to be Psi2 antibonding. And so now I can see that because, the HOMO is an odd-numbered molecular orbital, the LUMO over here is the even-numbered, and since one's odd, one's even, they're definitely not going to have the same symmetry. So here Psi1 is symmetric, Psi2 antibonding over here is anti-symmetric, so they don't have the same symmetry. So what should be allowed under thermal conditions should be the suprafacial-antarafacial. Let's take a look at that molecular orbital here. So again, HOMO on this one is symmetric, so the ends match. All there are ends in this case. So, but for the LUMO of the second ethylene molecule, it's antisymmetric. And so we see that we match on one side, we don't match on the other side. And so suprafacial is forbidden. So, but suprafacial-antarafacial would be what we call symmetry allowed, or usually just use the term allowed. But we have a problem here. So both these are only 2 carbons each. And it turns out that antarafacial is not going to work. So it turns out it works up here and for larger molecules because you have a lot more space to kind of distort the shape, if you will, a little bit to make antarafacial work for one of the reactants. So, but with both of them being just 2 carbons, turns out antarafacial is impossible. And so we say in this case that this one is geometry forbidden. And so that's why in this first case, if it were able to happen, it would be suprafacial-antarafacial, but because that's not possible for just, in this case, it's just ethylene with ethylene. Anything bigger, it'll work. So, but in this case, it's not going to work, and so we just say no reaction. All right. Now, if we do this under photochemical conditions, like normal here, we're going to promote an electron up to Psi2, antibonding for this guy. And so Psi1 is no longer the highest occupied molecular orbital under photochemical conditions. Psi2 antibonding is. And whereas Psi1 was symmetric, Psi2 here is going to be antisymmetric. And now the HOMO and LUMO of the 2 reactants are both antisymmetric. And with them both being antisymmetric, they now have a chance of lining up in such a way that we go from bottom to top on the left side and bottom to top on the right-hand side, and that is suprafacial-suprafacial. And so under photochemical conditions here, suprafacial-suprafacial is allowed, whereas suprafacial-antarafacial is forbidden. And so we do actually form cyclobutane in this example under photochemical conditions, but no reaction under thermal conditions. Cool. Once again, how would I tell if this had formed under either condition? Well, again, in this case, I have a dead way because in one instance, it would not happen at all. The other would happen. But outside of that, if I had a couple of different substituents on here, like let's say I had 2 cyano groups here on the one ethylene here that were cis to each other. Well, in this case, we see it's suprafacial-suprafacial, just like Diels-Alder is normally suprafacial-suprafacial. So in that case, then you know that 2 groups that are cis to each other would end up cis on the product. So if I tacked on another couple cyano groups here, well, then you'd go over here and be like, oh, if they're cis on the reactant, then they're cis on the product. when your transition state is suprafacial-suprafacial. And there you go. And you'd get a meso compound, so you wouldn't have to draw both, two versions, just a single meso stereoisomer. So that's how that could kind of come in relevance. And sometimes they'll actually switch this around on you, and they'll actually give you the reactants and a product, and then ask you some questions about the transition state. So for example, we'll form an 8-membered ring in this case with our movement of electrons. We'll still have a couple of pi bonds. Let's show our movement of electrons here. All right, so the question is, what's going to go on with those cyano groups? Well, in this case, I'm not asking you to predict what's going on. And notice I haven't shown thermal or photochemical here yet. But what I'm going to do is show thermal conditions. I'm giving you the conditions now, but now I'm actually going to give you the product. And so the product I'm giving you is this one. I'm giving you the product. Now, I haven't told you this is the major product or minor product. I haven't told you anything of the sort. My questions, though, are going to say, with the reaction written as it is it forbidden or allowed or forbidden? And was it suprafacial-suprafacial transition state or suprafacial-antarafacial transition state? So if we look at this, well, the first part is we can answer whether it was suprafacial-suprafacial or suprafacial-antarafacial just by looking at stereochemistry. Here, these two cyano groups are cis on the reactant and they're cis on the product. That's what suprafacial-suprafacial does. And so our transition state for this reaction would be suprafacial-suprafacial, which I'll abbreviate as supra-supra. Okay. Now the question is, was it supposed to be suprafacial-suprafacial under these conditions in a 6+2 cycloaddition? One way to think about it. And so, well, in this case, with a multiple of 4 here, this is, notice, a 6 plus 2 and 8 total pi electrons is a multiple of 4. And with it being a multiple of 4, that's opposite of what we'd see with Diels-Alder. With Diels-Alder, which is 4 plus 2 of 6 total pi electrons, that's a 4n plus 2 number. We know with Diels-Alder that under thermal conditions, suprafacial-suprafacial is allowed. Well, here, if this is then a multiple of 4 instead, then it should be opposite of what we saw with Diels-Alder. And so instead here, it actually should be suprafacial-antarafacial is what should be allowed under thermal conditions. And since in this case it's supra-supra, well, that's not allowed under thermal. That would be the allowed transition state under photochemical conditions, but not under thermal here. And so this is actually the forbidden product. So it'd probably be a minor product, not the major product. So that's the other way this could kind of be flipped on its head. Instead of having you predict a product, and again, if you're asked to predict a product, predict the allowed products, but I could give you a product and then ask you some questions about the transition state. Was it supra-supra or supra-antara? And was it allowed or forbidden? Cool. That is kind of the deal. And like I said, this takes a little bit of getting used to. Definitely want to work out some practice problems. But hopefully you have a much better handle on understanding this in the context of pi molecular orbitals. Now, if you have found this lesson helpful, would you consider giving me a like and a share? That will ensure that many other students get to see this lesson as well. If you are looking for the study guide that goes with this lesson, if you're looking for organic chemistry practice problems or organic chemistry final exam rapid reviews, check out my premium course on chadsprep.com.